Alright, so in this lesson we're going to look at what's called the parallel axis theorem, which is a kind of clever mathematical trick to deal with systems of objects or an object that's a uniform mass object that's not rotating through its center of mass. This can be used to calculate the moment of inertia about any axis that's parallel to one that goes through the center of mass of the object or the system of objects. And this is a shortcut that doesn't involve the use of calculus in order to do this calculation. And the way to do this is that I about an axis parallel to an axis that goes through the center of mass is equal to the moment of inertia about an axis through the center of mass plus the mass of the system of objects times h squared, where h is the distance between these two axes. So let's look at how this works in a couple of sample problems. In this problem we're going to revisit problem F9. And so if you go back and think about what this problem really was asking us, we had a rod with a mass 2m and two balls of mass m on either side of the rod. The length of the rod we said was length L, and the moment inertia, if this was rotating about the center of mass of the rod, is 2/3 ml squared. And you can go back and look at problem F8 to show yourself, remember that that is true. So what happens if we move the axis of rotation to the far left side of the rod? Remember, that's basically what we did in problem F9. So let's use parallel axis theorem to do this instead of the way we did it before. And so here we have the moment of inertia about the center of mass, 2/3 ml squared, plus the mass of the system, 4m, times however far that axis of rotation has been moved squared. And it's been moved L over 2, and so L over 2 squared becomes L squared over 4. If we kind of work that out, we get 2/3 ml squared plus ml squared, or 5/3 ml squared. Now if you go back and look at problem F9 in your notes from a few lessons ago, you would see that this solution is completely consistent with the solution we came up with doing it a different technique. So the parallel axis theorem works here. So say we look at a different situation. Let's say we have a ring with a mass m and a radius r, and instead of rotating about the center of the ring like we normally have, like the ring rolling about the center, we've instead got it to rotate about some axis of rotation that's on the outside of the ring. So imagine this ring rotating kind of this way about this axis of rotation where this point remains stationary. And I want to determine the moment of inertia about this axis of rotation. So the way I would do this is I is equal to I center of mass plus m times h squared. That's worth pointing out. The center of mass, or the moment of inertia about the center of mass for a ring, is mr squared. And the mass of the ring is m. And it looks like this distance is now r, so mr squared. So it looks like we now have a moment of inertia of 2mr squared. Which, if you think about it, really makes sense. It should be harder to rotate a ring if I grab some point on the outside and try to rotate it around than if I am able to rotate it about the center of its center, or if I can rotate around the center of mass. The next one I have is a solid uniform disk of mass m and radius r that's being rotated about a point that's halfway between the outside and center of the disk. And I want to determine the moment of inertia about this axis of rotation. So this distance is r over 2, and the thing to remember about solid uniform disks is about the center of mass is half mr squared. So we have half mr squared as that moment of inertia times m times r over 2 squared, and so we end up with is the moment of inertia about this center of about this axis of rotation is 3/4 mr squared. So parallel axis theorem becomes helpful is if I don't have a uniform distribution of mass about my axis of rotation, but the system itself is uniformly distributed about some axis of rotation, that I can calculate the moment of inertia about some unusual system of mass or some unusual axis of rotation in a slightly different way. So that kind of concludes our lesson on parallel axis theorem, and we'll kind of look at other ways to do this in future lessons.